Hello everyone, and welcome to AISC's Night School, Steel Construction from the Mill to Topping Out. Tonight is October 22nd, 2018, and this is Session 2, the Manufacturing of Structural Steel Shapes, presented this evening by Jim Schoen and Shane Vernon of Nucor-Yamato Steel. My name is Brent Liu. I am with AISC's Continuing Education Group, and I'll be moderating this evening's presentation. I want to introduce this evening's speakers, Jim Schoen and Shane Vernon of Nucor-Yamato Steel in Blytheville, Arkansas. Jim is a plant metallurgist and has been in steel manufacturing for 34 years in special bar quality and structural steel plants. His responsibilities over the years have included melt shop metallurgist, rolling mill metallurgist, and quality assurance supervisor. Jim served on ASTM, ABS, AWS, and AISC committees. He's a graduate of the University of Missouri-Rolla with a bachelor's degree in metallurgical engineering. He will be our second speaker this evening. But we'll start things off tonight with Shane Vernon, who is also a plant metallurgist at Nucor-Yamato Steel. Shane is active with AWS, including AWS D11 and D1M. As a committee member, he's a certified welding inspector, and as well, he's been part of the ASTM A102 committee member. He has 24 years of steel industry experience. Shane, thanks for being here, and I'll let you take it from here.
Thank you, Brent. Hopefully everybody had a happy Monday. We're excited to take you through this presentation on manufacturing structural steel shapes. We're going to do a little bit of chemistry, a little bit of process steps, and Jim is going to finish up with some metallurgy, so I'm going to present the first half. So with that being said, let's go ahead and advance to the next slide, please. And here we're going to go over the process overview, and again, we're going to wrap this up with some of the grades of steel that we produce. When you look at a big 1,000-yard picture of this, and we start in the scrap yard, where we load our raw materials into to be prepared to be charged into the furnace. Then we go into the EAF, electric arc furnace melting. We go into that, and we make the scrap liquid, and we'll take it next to the LMF, the Ladle Metallurgical Furnace. We perform the refining and alloying of the steel. After that process step is complete, we go to the caster, which is primary function is take the liquid steel and cast it into a solid semi-finished product, typically beam blanks or blooms. Those are then reheated in the reheat furnace to the rolling temperature. And we bring it out into the mill and we roll it in the rolling mill stands. And once it's cooled and gone to finishing and cut to finished length, we will do some testing. And that will take us to the next slide, please. So how do you define structural steels? For us, we describe it as side for bar size shapes. For most structural steel products produced in the United States, carbon is your 5 to 10 carbon range. We typically talk in points. We call it 5 to 10 points of carbon. This low carbon content is very good for toughness, ductility, and weldability. Of course, math, you get a little bit about 97, 98% iron. Some of the key elements, we're going to explain what they are and how they impact the steel properties that we're going to go over tonight. Chromium, copper, manganese, molybdenum, typically just call it moly, nickel, niobium or columbium, nitrogen, phosphorus, silicon, sulfur, titanium and vanadium, and also tin. The next slide, please. So a little bit of an overview of the key elements that impact the properties of structural steel. So as the amount of carbon present in steel increases, of course the steel increases in strength, but also you lose ductility and somewhat lose your toughness as well. So carbon in steel comes from both the scrap and from coke additions we put in the furnace, the Ladle Metallurgical Furnace. And primarily we keep it low because of its adverse effect on toughness and weldability. And we'll explain that in more detail. Next element that we're going to talk about is silicon. Silicon is a deoxidizer. We add that to take out the oxygen that's present in the liquid steel when we melt it. So it's just primary deoxidizer in structural steels and alloy steels. It has a different use, but we're going to limit our discussion tonight just to structural steels. On the next slide. Talk about manganese. It's the big hitter right below carbon. So after carbon is it's the most widely used alloying element. It increases the toughness of the steel, improves the strength. Typically has approximately a 1/6 effective ratio compared to carbon as far as strengthening. It does have a processing effect of taking care of the sulfur that's in the steel, so it improves the surface of the steel when it's rolled. But manganese, we're going to talk a little bit about this. The balance of all these alloying elements always affect the CE, which is the carbon equivalency, as it affects weldability. And we're going to discuss the CE formula there at the bottom. And if I would, I'm going to go to that right now. That's the CE formula. It's in the A992. And basically, what CE does is gives the user an indication of what the heat-affected zone hardenability will be and can potentially lead to cracks. So we look at those alloying elements and try to balance strength and weldability and ductility and all that. Of course, heat-affected zone cracking is also affected by the cooling rate of the steel, the preheat, the filler metal. But for us, primarily, we control it. Our portion is controlling it by the chemistry of the steel. So as we look at chromium, it improves the corrosion resistance of steel. It's a mild strengthener. You'll see this in A588, which we'll discuss in a little bit. And it's a negative effect to the weldability. So on the next slide, please. Talk about copper. So copper, typically in structural steel, is a negative element. Is residual element is in the steel when we melt the scrap, unless you're talking about 588, where we purposely add copper to improve the corrosion resistance of the steel. Nickel is a mild strengthener and hardener. It's also improved the toughness of the steel. Nickel is added structural steel shapes. It usually comes from the scrap. We typically don't add this in structural steel. Moly increases the hardness, strength, and wear resistance of our steel. And again, we don't add that intentionally in structural steel. It comes through as a residual from the alloys. And all these elements are contributors to the carbon equivalency formula that we discussed earlier. Next slide. So, in general, copper, chrome, nickel, and moly are considered residuals. They just come through our scrap, they get melted in, and they're just present in steel. We don't typically intentionally add those. And the residual amounts, they increase the yield and tensile strength by 3 to 4 KSI. We get a little bit of kick from them. Next slide. Now, vanadium and columbium, nitrogen, we bring those up together because they're all tied together. These are called microalloys. And vanadium strengthens steel mostly through grain refinement by making vanadium nitrates. They precipitate out when the steel is rolled. And it also counts against your CE. Columbium, niobium, same element. We typically use columbium as a term here in the United States, but it makes columbium carbides and nitrides, and again, it affects the final grain size of the steel after rolling. Now, nitrogen, which is an element that's in the steel, it's just dissolved into the steel from the air, atmosphere, and it's used in combination. That's what vanadium grabs a hold of. That's what columbium. They'll combine with that to make the nitride, which precipitates to the grain boundary, which makes the fine grain steel. Next slide. So, phosphorus. Typically, phosphorus is an undesirable impurity in non-piling structural steel shapes. We do our best to minimize that. There is one exception, ASTM A690. It's a marine environment piling grade. It's a case which phosphorus is added intentionally for corrosion resistance, but it negatively impacts toughness. And sulfur, again, sulfur is something we try to get rid of the steel. We try to process that out, and we'll explain that. And it's an impurity, lowers the toughness of the steel, and it's removed by adding lime and spar at the ladle metallurgical furnace to be removed. And we'll explain how that process goes next. Next slide, please. So how does this all pertain to the engineer that's looking at his MTR? Again, we live and breathe by this in our world, but top requirement here, kind of give you a table looking at the different things. A little bit busy. It looks complicated, but really it's not. There's only certain key elements that you need to understand and focus on, and we'll go through those now as we go through the processing later. But ASTM A992, the typical wide flange structural steel grade, A57250, you'll see that. You got the A588 grade B. Thank you, Brent. And then, of course, A36, the old standby. As you go down to the next line of the table, we start talking about carbon. So if you look at those, they're fairly consistent. It's got 0.3 carbon max. So the spec allows us to go higher. We typically don't run in that range, but we're allowed to by spec. And then we'll bring it up. Typically, we like to get our strength from our microalloy additions instead of by carbon because we want to have a steel that has a satisfactory Sharpie V-notch. So then we look at manganese next. That's a big one. It's a big addition. It's the biggest component of the alloying that we add in. So if you look at 992, it goes from 50 to 160. I'd dare say you're definitely about 1% on most stuff. Same with 572 and 588, about 1%. 836, you don't have to achieve the same strength levels. The manganese is typically lower. In the next line, we'll talk about phosphorus. This is where they're not alloys on this one. These are actually held to minimums. We don't want them getting out of hand and affecting the property of the steel, so the spec puts a max on them. So we have to stay under an 035 for 992, which is a little more restrictive than the rest. And the rest of them are at 040, which is pretty much a standard phos level. If you look at sulfur here, same thing with 992. It's a lower sulfur. It's done intentionally to help the properties of steel, especially Sharpie V-notch. And then 572 or 050, 05 max. So those aren't added. Those are residual. We try to minimize those in our processing. Silicon, again, it's just a deoxidizer used to kill the steel. It's got about a 40 max on 992, what it is. And then a range of them on 15 to 40 on 572, 588, 836 is 40 max. Again, just got to have enough silicon to take care of the oxygen that you add in the steel to make it a killed steel. And we'll talk about that again. We're going to keep bringing these up so that the idea of the topic gets transferred correctly. Now the next one is vanadium. That's our microalloy addition. A little bit of vanadium goes a long way. Same with columbium. Doesn't take much to have a dramatic impact on the properties. So you look at these are pretty low numbers. 15 max, 10 max, 5 max. So these are very little additions of these make a dramatic impact on the properties of the steel. You look at copper. Copper again is residual. We try to keep that down. A992 has a 0.60 max, 588. Now this is where it's a little bit different. 588 is weathering grade, so copper must be within a range to maintain the corrosion effect, the corrosion protection that we're trying to put into the steel. And you look at nickel, again it's residual in all the other ones but 588. Sometimes we add that to get the corrosion index number up. And chromium, 40 to 70 on the next line. On A588, again, we got to hit that range. We got to hit 40 to 70 to get the properties of corrosion. Otherwise, we try to keep it down. Molybdenum, again, it's residual. We got to minimize that. Get too much of that, steel gets very, very brittle. So we control that through our scrap recipe. We talk about nitrogen. That's just, again, that's so many ppms that we get in the steel making process. We test it on an analyzer. We'll talk about that later. But it's not specified, but it's present in the steel. Then we talked about maximum carbon equivalent. We kind of talked about that, how certain grades, 992 specifically, has a max carbon equivalent that we need to have. That's there to make sure the buildability of the steel is consistent. The rest of them don't have it specified, but it's probably specified supplementary, but it's not in the spec. Go to the next line. It talks about corrosion index. That is unique to A588. That's a calculation based on the chemistry of the steel. We have to hit this number, 6.0 or higher, to ensure that the corrosion resistance of the steel is termed a weathering grade. Again, we got the tensile strength, the big things we worry about: tensile, yield ratio, and elongation, those last four items there. I mean, I'm sure all engineers are pretty well familiar. Tensile strength, 65 KSI, typically all the way across. Yield strength, which 50 KSI is typically where all these products are produced at. Unless it's 992, which has a range, and has a yield to tensile ratio for seismic reasons. We want to have enough ductility in the steel, energy absorbed before fracture. So that's why that's written in there on that one. And it's interesting on the bottom, the elongation there, all pretty well consistent, 18 to 20s, which I consider a fairly ductile steel. Next, please. A new grade that's coming into the market that I think is a really unique, pretty innovative product. It's been out there for a while. It's really coming onto its own. We're seeing it specified more. But it's A913 quench and self-tempered steel. And the first thing is you look through the requirements because it's got different grades, 50, 65, 70. But look at that carbon max. You can see it, immediately see a difference right away, right? You got a 12 max versus roughly 20 that we saw on the other page. That's significantly lower. The manganese are a little bit higher because the carbon's lower. And then you look, the phos and sulfur are much more restrictive. Silicon's about the same. Vanadium, columbium, the standard grain refiners. Copper's all right, about 45. And the residuals are also restricted. But as you go all the way down to the bottom where it says max carbon equivalency, about towards the bottom third there, that is, you can see where the weldability of steel comes into play. And this is actually set by specification, a 0.38, a 0.43, and a 0.45. So as you go through that, and you see that as the strength goes up, we got to bump the CE up a little bit. But as the tensile strength, yield strength all go up, we're achieving this not through chemistry, but through basically the quenching of the steel, allowing it to self-temper. So you'll have a steel with the weldability of an A992, grade 50, but the properties will be similar to a grade 65. So this is a pretty innovative way of using basically a modified heat treatment process in process. This is done while we're rolling. And impacts properties that gives us a much more ductile steel, a much more weldable steel, and with no more alloy content that affects the weldability of the steel. So pretty exciting stuff. And this one's unique. It actually has a Sharpie V-notch. It's specified by the spec, the very last line, and that's unique. You don't see that everywhere. That is unique to that grade. So basically, you're mandating a certain level of toughness in the steel. So that's an innovative process in that, or aspect of that grade. We move to the next slide, please.
All right. Thanks, Shane. We're having a slight technical difficulty here. If we could pull into a quick private speaker conference so we can get that resolved. Thank you. Please stand by, everybody.
You're with your audience. Please continue.
All right. Thank you, Keith. Go ahead, Shane.
Okay, Brent. I think we've now finished that slide, and we'll go ahead and move to the next one, please. All right. Now we're going to start going through the electric arc furnace and operations. Again, we're taking cold scrap, ambient temperature, and we're going to get it up to 3,000 degrees F. So there's several beginning of this process is with electric arc furnace. We're going to charge it with scrap, and then when we get done with it, we're going to tap it into a ladle, which is basically a pot that's refractory line that basically is a carrier unit for carrying the liquid steel from one process to the next. Next slide, please. All right, so this is where we come into the recipe of how we make our steel. So there's different types of scrap, and we purchase them at different price levels, and there's efficiencies of using one versus the other, but I'd like to just kind of briefly go through the different type of scrap we're going to see. In the back left-hand side is the number 2 shredded, which that's all your old combines, cars, and everything that goes through a shredding facility, and the non-ferrous product is separated off, and the ferrous product goes to us to be melted. The benefit of this is it's very dense, loads very well, and the copper is sorted out typically through the non-ferrous separators. We don't have as much copper coming through that scrap. And in the front left, again, we go to number 1 heavy melt. It's our primary scrap type. Another primary scrap type, I should say. That's a premium product. It's very dense, very heavy, typically very clean as far as residuals. And then on the right-hand side, the lower right, is the plate and structural steel. That's just your demolition buildings, things like that. Anything that used to be an I-beam, we buy that. It's big, it's heavy, it's dense, but typically has a little bit higher residual level than the number 1 heavy melt. And then the number 2 heavy melt is basically everything else. It's your bicycles, washers, dryers, everything else that goes in the scrap supply chain. That's what we use there. And it typically has a little bit higher residual level than the other ones. And typically, the lower the residuals, the cheaper the steel is. So if we move to the next slide. So the scrap buckets are loaded by a crane on the outside, and we use a blend, basically a recipe. And in that recipe, we're trying to get the residuals as low as we need to make the product we're trying to, and achieve the optimal melting efficiency. Next slide, please. And here we should have a video. Brent, if you could start that, please.
There's no sound on this video. Just
And again, we just have a mobile crane that pushes the bucket around and picks up from various piles of scrap and just loads it per recipe. There's load cells on the bottom of that car, so the operator knows how much he's loading at any given time. All right, go ahead and advance to the next slide, please. So what is the electric arc furnace, and what are we talking about here? So this is a little diagram schematic of what electric arc furnace is, and it has multiple components. What I like looking at is a big three-phase welder, and these big graphite electrodes conduct the arc plasma between all the 3 phases and creates an incredible amount of energy and heat. Well, to contain this, we have a refractory roof that swings off so we can put the scrap in with the electrodes. We have water-cooled panels in the upper half of the shell that basically take some of the heat away so we don't melt the furnace down. And then there's the bottom half is all refractory lined with dolomitic type refractory. The scrap is in the middle. We have a slag door on one side that the slag goes out, and we'll talk about what slag is later on. And then we got the tapping spout or the tap hole on the other side where the liquid steel goes when we're done melting the scrap down. So let's go ahead and advance to the next slide. So the roof and electrode raise out to swing out for a charge. Go ahead and advance to the next. We bring the charge bucket in, and we bring it into the furnace and open the clamshells and drop the scrap in. So next slide, please. Here you see a picture of it trying to, sorry, I got a little error right here. Dropping the scrap into the furnace, and you see the fireball coming out. This is probably the most neatest part of the process, but the scrap goes in, and quite a reaction there. And go to the next slide, please. And I believe we have a video here, which is live, and I'll go ahead and play that, and I won't talk through it. Okay, can you please advance to the next slide? So besides scrap, we have some additions we put in the furnace with them, lime and carbon, and we add those during the melting process as well. We'll go to the next slide, kind of explain the reasoning for that. So what happens in the furnace besides just melting? And we're going to talk about some of the oxidation potential of various elements in the scrap. Some of the elements are oxidized and go out in the slag, others remain. But basically what we're saying here, when you think about the electric arc furnace, that's an oxidizing process. When you go to the ladle metallurgical furnace, it's a deoxidizing process. So the high temperature thermochemistry reactions there are two completely different processes and different routes of what we're trying to accomplish. So as we go to the next slide, we'll go through that in a little more detail. So when you look at the elements that are in the scrap that we're melting, we get the top third there. These are elements that readily oxidize. They disappear very quickly from the liquid steel and go into the slag layer, and they're gone. The next ones towards the bottom, manganese, carbon, they take a little bit more energy, a little bit more oxygen, and then they also go to the slag layers. Now, the bottom three never go to the slag layer and at the steel baking temperatures that we work at. So once tin, nickel, and copper get into the liquid steel in the furnace, we cannot get them out. So go to the next slide, please. So we keep talking about the slag, and this is a crucial part of steel making. If you understand slag, the steelmaker takes care of the slag, and the slag will take care of the steel. A little quote there at the bottom. But that is very true, because that's how we control everything, is through our slag processing of the steel. So basically it's metal oxides, impurities in the steel that float to the top because they're less dense. We add lime, and when we say lime, we say high-cal lime and dolomitic lime to get the chemistry of the slag that we want, and so absorb the impurities in the steel that float to the top. And oxides, they should previously been in the charged scrap that meld in with the steel. That's where they could come from. They come from that as well. So we'll talk about the slag process in the next slide. So that's multifunctions, very crucial. There's some practical needs, and there's also some needs of just the slag processing of the steel, I guess. So you got to slow the temperature loss because you can't have heat radiating out all over. It protects the furnace walls from the arc because the arc plasma is extremely hot, high energy. We have to control that. And it covers this electrode arc to increase the efficiency and slows down nitrogen pickup. Now we talked about nitrogen before. But actually what happens is ambient air flows through the arc plasma, the nitrogen gets stripped and actually gets absorbed to the steel. So we get so much, but we can't have too much. We got to control that. The slag also, very important, absorbs the phosphorus. So this is where we get rid of the phosphorus in the steel, is through the EAF slag and the oxidizing environment. So it also has to be pH balanced, essentially, so that it doesn't eat all up the refractory of the furnace. So we have to contain proper amounts of MgO and CaO, which are basic, to maintain the right slag pH. Next slide, please. So dephosphorization, again, a key part of the electric arc furnace process. It needs to dephosphorize the steel to get it out. So to make that happen, we have to have very high FeO and MnO levels in the slag to provide the oxygen for the reaction. And basically a little chemistry there, but what happens is the lime, CaO, grabs the lime or phosphorus oxide, absorbs it in the slag, and removes it from the steel. Next slide. So here's a picture of the slag coming out of the slag door. As we run the heat, the slag builds up, starts foaming out the door. And when we use that, basically a sense of flushing of the impurities out of the furnace. Next slide. So we like to have this slag foamy. We do this by a couple different techniques. The primary one is we use injection carbon. So the slag should be high enough to cover and protect the furnace wall and electrode arc. We want to do that again. And it increases the energy transfer from the slag to the steel. The arc, Buildworks does that. And it helps remove the slag due to the increased surface area. The slag, increased surface area, helps the removal of impurities. Next slide, please. So slag foaming, how is it done? So the carbon is dissolved from steel, scrap, pig iron, and other charged carbon. Oxygen is ejected through the lances on the side of the furnace. So basically you're making a carbonated slag, for lack of a better term. So CO, CO2, it fluffs up the slag. We have to maintain the right chemistry to get the right viscosity so it foams up. And not all the oxygen finds the carbon. Some of it oxidizes iron, which makes FeO, which ends up being yield loss to the steel processor. That's a loss of the product for us. Next slide, please. So basically, fine carbon is injected through the burners at high velocity. It reacts with the Fe and CO bubbles, and then it makes pure Fe and CO bubbles. The Fe goes back into the steel. The CO bubbles up. And the small particles of magnesium oxide, we talked about high cal and dolomitic lime additions. The dolomitic lime has the MgO, the magnesium oxide, to assist with this process. And they take time to flow through. It depends on the viscosity of the steel. You don't want it or the slag. You don't want it too thick. It can't bubble up, or it's too thin, and the bubbles just pass right through without increasing the surface area of the slag. Next slide, please. The other thing, we talked about the oxidizing environment, and if you look at the graph on the left-hand side, it's pretty key. You know, we got to be able to understand that concept. But on that graph, as the percent of carbon goes down, the percent of oxygen in the steel goes up exponentially. So if we tap, typically we can tap, you know, about a 4 carbon, we'll have almost 600-700 ppms of oxygen. But if you inject too much oxygen, you'll be way up there, and you'll have almost 1,000 ppms of oxygen. We control that because we oxidize the steel. It oxidizes iron, and that's yield loss. So we have to control that. Next slide, please. So once we get to the right oxygen level, right temperature, right carbon level, we'll go ahead and take a sample, confirm that, and then we'll rock the furnace over and we'll tap it into the ladle. And then this slide shows a picture of us tapping into the ladle again. That's just a refractory lined vessel that we transport around the shop to carry the liquid steel. Next slide, please. So we have a process we call a tap it open. It's the terminology we use now. So it means we don't kill the heat. We don't put any deoxidizers in the steel at tap. We let it happen at the ladle metallurgical furnace. We do that for a couple reasons. One of our primary is to lower the nitrogen pickup. So if there's lots of oxygen in the liquid steel, it's less susceptible to absorption of nitrogen and increasing the oxygen or nitrogen levels in our steel. And then lower the carbon content. Again, we want to keep our carbon as low as possible to achieve the properties we want as far as yield, tensile, and Sharpie V-notch. Next slide. I believe we have a video here.
Yeah, with this next video, there will be no sound coming across, and that's for the remainder of the videos this evening. There's no more audio on the videos. So with that, we'll go ahead and push play.
I'll try to narrate real quick. This is a sped up version, but we'll pick the bucket up, and you see the crane pushing it in. Again, we'll bridge it over. Operator will bridge it over. Electrodes come up. Roof swings out. Crane operator will bring the charge into the furnace. This is the cool part. Charge is dropped. We get the bucket out of the way and swing the roof in. Now we'll lower down, we'll start the bore in. Basically, we'll bore into a slag, and then we'll start slagging off the heat. Roughly, the whole process takes us about 28 minutes, 30 minutes, somewhere in there, from charge to tap. Now we're going to the tap side, tapping the heat. And that's it, sped up version of the electric arc furnace process. Go ahead and advance to the next slide, please. All right, so next step we have is the ladle metallurgy furnace called the LMF. So basically from an open heat, when it's wide open, we have no chemistry adjustments made at tap. We bring it down to LMF. The schematic on the left kind of gives a side view of the LMF. Now remember that ladle that was transporting the liquid steel, that's what you see in the center. And it's stirred through an argon plug. Let's start at the bottom. You got a plug comes in there. We use argon to stir the steel. And then you got a liquid steel layer. Then right above that is the slag layer, which is, again, high cal lime with some flux additions added, and you got the electrode arms coming through the roof. They're arcing on the top, and the roof is water cooled, and it's all sitting on a trolley car so we can slide it in and out. If you look at the picture on the right, you can see the rails so that we could have ladle on either side of the LMF, bring one in, kick one out, depending on what we need as far as moving ladles and steel around the furnace and the melt shop, rather. So next slide. So this is where the heart of the metallurgy happens as far as the chemistry additions of the steel. So we receive the metal and slag from the EAF. We're going to kill it, and we do multiple things at the same time. We're going to heat it up. We're going to alloy it. We'll get the sulfur out of it, confirm it's in spec. If it's not, do it again, and then if it's ready, we ship it to the caster. And in all steps, we control the slag. We stir intensity is controlled, and we periodically measure chemistry and temperature while we're doing that. Next slide, please. So there's many functions that we got to do at the LMF, and part of it is we cover some of the Fe, iron, and manganese from the EAF carry over slag. So when we tap, some of the slag that's in the furnace goes to the ladle furnace, goes into the ladle furnace. There's some oxidized iron and manganese in there. We can actually get a little bit of that out as a yield gain. Very small percentage, but it is there. Our job is now to deoxidize the steel. Like I talked before, the EAF is a oxidizing environment. The LMF is a deoxidizing environment. Once we got the heat killed, we now desulfurize the steel. We're going to alloy the steel to the proper grade spec. We're going to rinse it through the porous plug, argon stirring on the bottom of the ladle, and modify the inclusions of the steel, and achieve the temperature needed for casting, and act as a buffer between the EAF and the caster. Next slide, please. So I have multiple additions we do at the LMF. The first one, of course, is the inert gas, typically argon. So we're going to stir that up with argon on the bottom. Sometimes you can top lance it, but that's kind of an old practice. Typically now it's all done by bottom pour, or bottom stir porous plug. And at the end of the process, we usually gently stir the steel to float out some of the inclusions. Calcium carbide is something we add as well. Its job is to kill the slag and get the FeO out of the slag and MnO out of the slag and have a report back to the steel. It's important for also improving basically the pH with the chemistry of the slag so it doesn't attack the brick. We add lime, high cal and dolomitic lime, again, to create the flux, the slag layer. And then we use fluorspar, calcium fluoride. It's basically a catalyst that fluxes the steel, makes it thin out quicker, and it aids in the desulfurization of the steel. Next slide, please. All right, so then we're going to add our ferroalloys. We don't add pure manganese, they're always alloys. So ferromanganese, ferrosilicon, silicon manganese, ferroniobium, ferrovanadium, ferrochrome, all come as a ferroalloy. And we add that to achieve the chemistry for the desired grade. We add ferrosilicon and silicon manganese to kill the heat, get the oxygen out. And we balance, aim at the minimum alloying elemental levels to get the strength we want, because if we add more, we're wasting money. We use microalloys, niobium and vanadium, precipitate, we talked about that before, strengthening and grain refinement. And they combine with carbon and nitrogen, so this is where we add those. The oxidants, typically, sometimes silicon killed is what we primarily produce in the United States. Sometimes aluminum killed, but not as often. And we remove the dissolved oxygen from the steel. The oxides are lighter than the steel, and they float to the top during the stirring process. And we also add cord wire, typically calcium wire, and we use that for inclusion modification and aiding deoxidation. Again, silicon takes out oxygen, the calcium wraps itself around the inclusions that minimize their detrimental effect when rolling. And it's another method for alloy additions and deoxidants if we need to do that. Next slide, please. So this one's kind of interesting, and I hope you bear with me, but what we do here is we use optical emission spectroscopy to analyze the steel chemistry. So what we'll do periodically during the processing of the heat is we'll stick a sampler into the steel and create a steel lollipop, which we grind. We'll put it on a optical emission spectrometer, and basically an arc is generated between the electrode that's in the machine and the steel sample, and simple extra, diffraction of the light breaks it down to individual wavelengths of the element you're looking at, hits the detector, and we know what our steel chemistry is. And it's a pretty powerful tool, use it every day. So if you look at the very top here, we're kind of showing you our process of a heat. So if we go to the very top line of the chart there, heat 1, 2, 3, 4, 5, 6, there we go. So it shows a sample initial, it goes LMF2, and what I want you to kind of look at is you look at the carbon, manganese, phosphorus, and sulfur, not so much phosphorus, but you look at those elements. As we process the heat, the carbon goes up a little bit, definitely the manganese goes up because we're trying to get the alloy additions in there to get the strength we want. Phosphorus and this one's pretty much staying the same, but the big one I like to see is the sulfur. You see the sulfur's being worked down. We're working that down by the slag additions that we're adding. At the same time, right next to it, the silicon. We're adding silicon to kill the heat, and you see it had none before, then we add it when we get to 0.20, which is typically the silicon levels we run at. So that's the heat as it's being progressed in time and the elemental adds we make to get the properties of the steel that we want. Next slide, please. All right, so here we go, typical changes in the composition during A992 processing, again the standard wide flange grade that we make the most of. Like we talked earlier on the previous slide, the silicon will increase since we're trying to get the oxygen out, so we add silicon to remove oxygen. Manganese, vanadium, and niobium are also added to be increased, and sulfur will decrease as we process the heat. Next slide. So functions of the LMF slag are to absorb inclusions, desulfurize the steel, thermally insulates the steel, prevents reoxidation, prevent nitrogen pickup, protects the ladle's refractory from being attacked, and also protects it from the arc of the ladle furnace. Again, make the slag, make the steel. Next slide, please. So a kill the heat, we just basically when somebody says a fully killed heat, well, any steel produced today better be killed. So you try to get the oxygen out, we add silicon to remove it. It's a standard addition, but occasionally aluminum is used. But sometimes you hear that term killed steel. Well, that's all it says, you add enough silicon or aluminum to remove the oxygen from the liquid steel. Next slide, please. Simple silicon reaction plus oxygen grabs 2 atoms of oxygen from silicon, makes silica sand, which floats to the top and gets sucked up into the slag, and it's gone. If it doesn't get out, it does make inclusions. You'll hear about inclusions in steel. We can't get all of them out, but you get most of them out. And aluminum is very hard to do because you got to be very careful with it. You can cause casting problems, and we call it a term called choking, where it'll terminate the cast, and we don't want to do that either. So next slide, please. So how's desulfurizing done? This is the key component of the ladle furnace, what it's supposed to do, one of the key components. So we've got to get the sulfur down so we improve our Sharpie V notches. It improves the castability, minimizes cracking of the semi-finished product. So basically on the left you have a little picture of a ladle, you got the bubbles running up, you got the slag layer on the top, and that slag metal interaction at that interface is crucial, and that's how we get the sulfur out. So you got iron and sulfide that's in the steel, and a lime and a liquid lime in the slag, and you got FeO and calcium sulfide in the slag. So basically what we're trying to do is work everything to the right where we make calcium sulfide in the steel, and the FeO we'll take out with the calcium carbide. But you got to have enough slag to make sure it's not super saturated, because eventually it's a sponge, the slag is, and if it gets too full of sulfur, it'll stop working. It can't take any more. So you got to have enough lime in there to make enough slag to remove the sulfur. It's got to be liquid, can't be solid. It's got to be basic, but not too much calcium oxide, and it has to be deoxidized with calcium carbide. Next slide, please. All right, so impact of the stir time on inclusion content. Worst time is money, so basically we try to minimize minimum amount of stirring we got to get is 10 minutes to float out the maximum amount of inclusions. Just a cost relationship there. Of course, the longer you stir it, at some point you're going to get to a level where you can't get any more out, and we don't stir past that. But it's kind of neat to see once it drops really quickly in the first 10 minutes, but after that, don't get as much bang for your buck after that. Next slide, please. This kind of shows some of the technology here. We've got an operator getting a sample. It's a wireless thermocouple. Basically, there's a disposable cardboard thermocouple on the tip. He sticks it in the steel. Top right-hand corner, you can see that you got a temperature of 2865, which is wirelessly transmitted to the pulpit. And so we check the temperature. Next slide, please. Now we have the continuous caster, and like I said, the primary function of the continuous caster is to take liquid steel and make it solid into a usable shape. Kind of a side view on the left-hand side. Middle picture is more of a picture of the strands coming through the straightener, because it comes out of the curved section, we have to straighten it. And the right-hand side shows a bunch of beam blanks stored in inventory, which is our ultimate goal prior to rolling. Next slide, please. So the casting, it's the highest elevation in the shop. It's a pretty neat process. On the left-hand side, you see a picture at the ladle, probably at the highest level in the shop, full of liquid steel. Going to the caster, so kind of a schematic on the right-hand side. You got the ladle. The steel will go through a ladle shroud, because at this point we want to protect the stream as best we can from outside air getting into it. We want to keep the oxygen away. It goes into a reservoir called a Tundish, which holds a small portion of the liquid steel. Thank you. And what that does, it distributes the liquid steel over however many molds we're running. Sometimes we're running 4 molds, 1 mold, 2 molds, depends on how many we got. So when it pours out, it goes through, some shops will go through some sort of submerged entry nozzle. It can be open stream. Depends on what grade of steel you're making there. It'll go into the mold, which is a copper-cooled mold. It oscillates up and down as it holds a certain level. What's interesting about a continuous caster, it's not solid when it comes out the bottom. You basically have an outer shell that is solid, an inner core that is still liquid, that proceeds all the way down to the end of the machine, and we call that, the end of it, the metallurgical length. And the metallurgical length better end before you get to the torch, because you about imagine what happens if you cut the core, it's still liquid, shoots out the end. So we don't want that to happen. That's a bad day. So next slide, please. So steel from the ladle is fed through a ceramic tube. We call it the ladle shroud. What's important, there's a couple important things there. You don't want to get the level too low, because you can actually vortex slag into the Tundish. So we actually shut our ladles off a little bit early to make sure we don't suck any slag into the Tundish that gets into the cast product. We use a slag gate to control the flow of steel. Think of a refractory metal or slide gate. That's about what it is. Gate valve, same thing. And like I said, the Tundish distributes steel to each strand of the caster, and it flows into a water-cooled copper mold into the desired semi-finished shape. Next slide, please. So ladle shrouds, on the right-hand side, you see the glowing tube next to the operator there. Its primary job, again, is to keep oxygen from getting to the steel. What you're seeing there is 2 ladles on a turret arm. He's operating on one. There's the shroud, thank you. And his job is to make sure, we got to insert that manually, so we hook that up there with a manipulator arm. We open the slag gate, and then we let it run. It pretty much positions itself, but once you got to hook it up initially by yourself. Sometimes gaskets get added to achieve a good seal in some shops. Next slide, please. Here's the Tundish, kind of an overview schematic of the Tundish. It's a buffer. So we're continuously casting, so something has to be a little bit of a reservoir there while we're swinging the other ladle into the casting position. So this will hold 15, 30 tons, depending on the size of the Tundish. And just a real quick overview, but you look at it, it's got dams and weirs, impact pads, so as liquid steel comes in, it's distributed uniformly. So the goal here is to each strand gets steel at the same temperature and the same chemistry to each one. You don't want a short circuit event where 2 strands are hotter than the 2 outside strands. You don't want that. You want the steel temperature consistent across all the strands as it goes into casting into the molds, so we have a quality product. And go to the next slide, please. The Tundish is kind of a delta shaped. The picture on the left-hand side shows we call that the running line, the wear liner. It is consumable, so we'll take it back to a safety lining. That's what you're seeing right there. It's a torn out Tundish. On the right-hand side, upper right-hand corner, you'll see a Tundish that's sprayed and ready to go back into service. The steel running on this is corrosive. We'll actually lose some of that, and it'll go away. So that's why we consume some of it, and then we come back and replace it after we tear it out. The middle picture is the Tundish. You can see there's a flux on top of that to prevent oxidation, and the liquid steel is going through the shroud and then being distributed by the Tundish to the caster molds. Next slide. So, like I said, it depends on what kind of shop you're in, what your Tundish design looks like. A flux is added to the top, again, to seal it off from outside air. Silicon-killed shops will generally use metering nozzles, control the mold, Tundish to mold flow. And aluminum-killed shops will use stopper rods or slide gates. Basically, aluminum is very sensitive to oxygen. You got to have that really, really sealed up well, or you're going to have big problems trying to cast it. So they have more sophisticated flow control devices just to keep the outside air from getting to the steel. Next slide, please. Also, it's done at open stream, like silicon-killed shops where surface quality is not critical. And to lubricate the mold, we can use mold powder or oils can be used. Next slide. It's the casting mold. The typical mold features is a water-cooled copper mold face. It's usually plated. Excuse me. This allows for the rapid heat removal from the molten steel to create this solidified shell. And the shell must be thick enough to contain the liquid before it exits the molds, and that's very important. In the mold oscillation, the mold moves up and down to keep the solidifying shell from sticking to the mold. And then the taper, so the mold taper has to match the shrinkage of the steel shell as it's solidifying through the caster mold. So it has a specific taper depending on the grade of steel that you're producing. And different grades of steel require different tapers. Next slide, please. All right, so on the left-hand side, you see a water-cooled copper mold. You can see the top right-hand side, you can see the semi-finished dog bone shape in the copper mold right there. And the middle section, you'll see actually we're pouring 2 streams of steel right into the mold web, into the web flange intersection right there. And we use that to make sure we have a uniform flow. If you stuck it right in the middle, we wouldn't have sufficient flow to the toes of the beam blank. So we use 2 streams. And we call it open pour because you can see the stream of steel coming through. And there's collector nozzles on top of the mold. That's what you see, the little refractory dishes there on the top. And they seal the liquid steel as it goes into the mold, and there's mold powder inside that to keep the air from that steel in the mold. Next slide, please. So you got the function of mold oils and powders. Number one, to provide lubrication. You don't want the liquid steel sticking. You don't have a breakout. And it also has absorption of non-metallic inclusions. Both oils and powders can do that. It's thermal insulation, prevents reoxidation of the steel. And heat transfer, controls the heat transfer so that we have proper shell solidification to the mold. Next slide, please. Here's just a quick diagram of the solidification of the steel, heat flow, and continuous casting. Again, like when it's in the, you see the mold there, and then you got mold powder that creates the interface as far as the between the solidifying solid shell. We call it the mushy zone, which is semi-solid, semi-liquid, and then a liquid core in the middle of the steel, in the middle of the mold. Next slide. And here we have the secondary cooling containment, because we mentioned before, was exit the molds, it's not solid, it's liquid in the middle. So we have to bend it, straighten it, and solidify it the rest of the way. So there's spray risers all the way down there spraying on the steel. There's rolls that are guiding the steel through the machine and straighten it. We have hydraulic straighteners at the bottom to straighten it out from the curved radius that it got to the caster. Next slide. So we have secondary cooling and containment. It extends from the bottom of the mold, and we have these rolls that keep compressive force on the steel, so we don't have any bulging. If the ferrostatic pressure exceeds the strength of the the shell, the steel can actually, liquid steel can penetrate out, and we call that a breakout, and that's a casting terminating effect. We don't want that to happen. And next slide, please. And here's some pictures of we call them mold segments. So these are pre-built, and they come in, we install them. They got a series of rolls that are gapped at certain distances. They close down on the steel, and they guide it through as it's being through the machines. And we basically insert these into the machine depending on what size of product we're making. We'll have different rolls, different gaps. So we have a containment chamber and containment rolls inside the mold segment. Next slide. Again, here's a picture of the spray chamber. We have sprays running down there, a really hot, humid area in the machine. And basically, you're trying to keep that cooling curve consistent as the machine's going, the steel's going through the curved section of the machine. Next slide. And here's the end product. We cut the beam blank with torches to the length. What's interesting on the right-hand side, you can see is we're actually casting two different beam blanks at the same time. It doesn't have to be the same. We can cast different ones at different times. And it goes out onto a cooling bed where we identify it, tag it, and put it into inventory. Next slide, please. So we have various finished, semi-finished cast shapes. We got the blooms, which are long rectangular sections. You got your billets, which are square. You have slabs, are just really thin and rectangular. And then the beam blank. This is the dog bone shape, which is a very innovative part of the casting process. And that's typically what most of our beam blanks in the United States are produced by, is through the dog bone shape. And next slide. And now I'll transfer it over to Jim, and he'll finish up the presentation.
Thank you, Shane. Shane just covered the area of the process that delivers the beam blank to the proper chemistry and surface quality so it can be formed into the finished product that everyone's familiar with, those being channel, angle, wide flange beams, S sections, and so forth. Next slide, please. There's two main types of rolling mills. The reversing mill, as the name implies, would be basically the beam blank when it just moves back and forth, and at each pass the gap is decreased until you get to the web and flange thicknesses. Now there's different types of reversing mills, which we're going to cover here in a minute, and then also the picture on the right side is what's called a continuous mill. As the name implies, that would just be the beam blank going through a number of different stands, and it just goes through one time rather than moving back and forth as a reversing mill would be. Next slide. Now these are the type of rolls that we're going to go over real quickly, what some of the different types of rolls are in the process. This is what would be called breakdown mill rolls. These rolls basically get the product in, basically get the beam blank into the product family. In other words, you're approximating the section depth and approximating what that flange height would be. You're not doing a lot of work on that thickness at this point of the process. You might even be spreading that beam blank a little bit. If you've got a, if you wanted to finish with a W24, but you've got a beam blank that might be closer to a W20, you can actually spread it with this breakdown mill. The breakdown rolls basically permit you to use a small number of beam blanks. Say a shop produces 10 different beam blanks, but maybe makes it into 100 different products. So there's not a lot of elongation occurs on this portion of the process either. You're just going to be, like I said, just getting you into product family. Next slide, please. These are another type of roll that's used in the mill. These will be used in the same rolling mill, just the different stands have different types of rolls. The main one was the universal rougher, is basically a set of horizontal rolls along with a set of vertical rolls. And again, the vertical rolls would hit the outside of the flange face, and the horizontal rolls hit the inside of the flange face along with the web. And as the bar reverses, for example, it would go in a reversing mill, those gaps would get narrower. On a continuous mill, each stand would just have a little narrower gap, you might say. And then an edger mill accompanies the universal mill, the universal roughers, but they are working the flange tip. You always notice on your wide flange beams you get that squared up toe, and that's because of the work that the edger mill does. Now when we put all of these stands together, you're going to get different configurations of rolling mills, and that's what this next couple of slides are going to show. Next slide, please. This is an example of a setup. It varies from plant to plant how many stands they would have. For example, this would be an example of continuous mill setup. And there's the point is every piece just moves through one way in this particular setup. These being you can see the flat rectangular pieces on here are actually how I'm demonstrating what the edger rolls would look like, and of course the circles being the horizontals, and the small ones that you don't see any rectangle on, those would be what I'm representing the edger mill there. But the point is, it's just multiple stands where it's just going through one pass. Next slide, please. And this is an example of maybe what a heavy section mill would have. Some mill that may run from a W12 all the way up to a W44, for example. They may have a breakdown mill. Some shops would have more than one breakdown mill even before you get to the universal rougher edger. And again, you can see the arrows denoting the direction of the bar. Breakdown mill on the far left, it's a reversing mill, where the bar goes back and forth. The universal rougher edger, again, the bar goes back and forth. Now you look at the finishing mill, that's just a one pass through. Basically that finishing mill would just be used to square up the flanges and just give it just a real light work. It kind of just the final little bit of work that's needed for that piece. Next slide, please. And this is some of the pictures of the process. This left picture is a beam blank being charged into a reheat furnace. Again, that beam blank comes from the melt shop, and it is identified. The tag's going to burn off, of course, in here, but the computer tracking maintains that traceability. This, of course, is the operator pulpit, and you can see on the operator's left, which in the lower right portion of the screen of the slide here, you'll see a barcode being read. So the automation is reading the exact identification of that piece. If you order Sharpies, for example, that's going to come in handy to know what the tonnage level is if you order a P frequency Sharpie based on the number of beam blanks and what that identification is. That all feeds into your piece or H frequency when you order a Sharpie. All that identification is maintained and so forth. Next slide, please. Now this next area, when a beam blank is heated, the entire furnace is not all ran to the same temperature. We want to ramp that temperature up slowly. The left side of this graph, this is a heating model that is used in was an example of a heating model that's used in a modern steel making plant. The left side denotes what the entrance temperature would be. That would be the door that takes the cold beam blank on the left side. The right side, after it walks by, the right side on this graph represents, in this case, an 81-foot furnace, which is 972 inches. And there's walks. There might be 20 beam blanks across the whole, you might say, x-axis of this graph here. And you just imagine a bunch of beam blanks in the H position all along this x-axis. Imagine seeing a bunch of H's there. And if you look at the model here in this particular beam blank size, you have a target temperature, which are the green circles, for example, and you have the piece temperature, which are the orange in these cases. So this is pretty much a furnace being run in automatic. If the mill, for example, goes down, the operators might have to take her down to manual, and these heating patterns would look slightly different than what you're seeing here. But those are always temporary conditions. When they turn the process over to auto, this is what a typical heating model would look like. Next slide, please. And I have a picture here of a beam blank coming out of the reheat furnace, out of the discharge side of the reheat furnace. You're going to see it lifted out in this yellow box that's on the left lower corner. That's called a descaler, and that blows off the oxides that formed at the high temperature, basically iron oxides that form. If you're in a weld shop, for example, that you kind of have some slag, you kind of have that those oxides from that weld building up when we're done, or even with a heating torch, you have oxides build up from those temperature reactions. That's hard on the surface quality, and it's also can damage the rolls. So we like to minimize that scale when it goes into the process. So again, this is a beam blank going through the descaler. So this next step that this beam blank is going to go through will be the breakdown mill that we talked about earlier. Next slide, please. Here's where we left off at with the beam blank exiting the descaler, and this larger picture on the right-hand side is the breakdown mill, and you can see the manipulators that's guiding the beam blank. That's because a typical breakdown mill can have different portions of the roll doing different work. So this beam blank might be, once it exits the other side, it would possibly be brought over to another portion of the roll. Maybe these manipulators move over to the right, for example, and using the different portion of the roll would do different work. And you can see a couple of shots of the pulpits here. In the upper right-hand side, we have a breakdown mill pulpit shot, and the lower left-hand side is a picture of the universal rougher edger pulpit. Now there's screens on here that denote the thermal imagers. Now Shane talked about vanadium and columbium, and also nitrogen. Now those are grain refiners, and in order to optimize those grain refiners, we have to do what's called controlled rolling. That would be on the next slide, please. Now this is an example of some of the instrumentation or some of the data that can be collected in a modern steelmaking process. These pass numbers are denoted. For example, pass 1 is that beam blank moving north in the universal rougher edger mill. Pass number 2 would be that beam blank moving south. Okay, and in each case, the gap has gotten narrower on the horizontal and vertical rolls. Pass 3 is the bar moving north again. Pass 4 is the bar moving south. These red and blue lines denote what each flange temperature is. So you'll see that there's points where there's no temperature being taken because that beam blank is simply moved out of the way of the thermal imagers. But let's look at when we get to about pass 10. Do you see where we have the red line? That's our temperature drop on a flange, and the blue line is a temperature drop on the flange. Now it's set in the computer, for example, on this particular product, what the hold temperature is. In other words, we're trying to get that temperature down to where those vanadium and columbium nitrides, whichever grain refiner we're using, will precipitate and form and will be able to act as the grain refiners we're intending them to. So this is hooked up to the computers that bar will not advance until that temperature is hit. We call this, in this case, the hold pass. We want a certain amount of reduction left while before that bar advances, and it has to be a certain temperature. Next slide. I believe this is a movie. Now this will show. You'll see at the start of this movie here. You'll see a bar that's at the universal rougher edger mill. Now that would be, for example, an even pass, the bar going south. Now we're going to also pan in this video. You're going to see a bar coming out of the breakdown mill that's going to be on your right here. Now here's a bar coming out of breakdown mill. Now this bar coming out of breakdown mill, it's going to be going to the next mill in a little bit. It's got a few more passes to go, and then meanwhile though, the bar that went ahead of it is being worked at the URUE. And here's where the real elongation's going on here too. You'll see the bar getting longer and longer in each case. Now this is this is the one where I was thinking of. It'll be the next pass where you'll see it advance to the next end. Now you'll notice that we actually have a longer bar in this case than what we had basically the run out table for, and that's to optimize the yield. The fewer beam blanks we have in a heat, the less noses and tails we have to take off that. So that's a way that to optimize the yield where steel remains the material of choice because of the cost. Because of yield, better yield is improved cost. Next slide, please. And this was one of the grades that Shane talked about, A913. We've talked about before what the controlled rolling does for us. Here's a case though where the A913 grade is where we're cooling it. After it's done rolling, it'll be quench and self-tempered. The typical A992, 572, and A588, those would either be as rolled or control rolled. In the case of heavy structurals, the vast majority of them is going to be control rolled because the bleeding the heat off and trying to hit Sharpie properties, you just about need some sort of controlled rolling in place. But this, if you look at the squiggly lines on the control rolled, you'll see where the bar is being rolled, and then you'll see the pause that we seen on that graph earlier, and then you'll see rolling continue again. If you can go to the next slide, we'll blow this up again. We'll blow this graph up. Here we go. This is the self-tempering temperature. In other words, we do all the control rolling. The quench, that's what we see, this real steep line dropping down to below what we call a Martensite start temperature. And then there's a self-tempering temperature. In order for the steel to be certified to A913, that self-tempering temperature, that rebound, has to be between 1100 and 1300 degrees. We go to the next slide, please. And this is another quick look at what's happening during the quench and self-tempering process. The bar at this point, at the very first point where it's orange, has not been quenched yet. Now you'll see the temperature drop, the yellow line representing and that's the second little graph, representing the outside of the piece, the red line representing the inside of the piece. The cooling effect hasn't affected the inside temperature yet, but when you look at the third graph by now, you'll see that the inside temperature, the red line, is starting to be drawn down. So by the time you hit the fourth graph, you'll see where the self-tempering is actually happening. It's the surface temperature is going up and the core temperature is going down, the red temperature is going down, and that's the point where we need to hit that surface of 1100 to 1300. Next slide, please. And this is another quick look at what's happening. The QST surface being a tempered martensite, then mid-thickness, we have a little bit more grain fine going on, but the control rolled mid-thickness would be a little bit coarser grain. But this is a good look at what's happening in this process. Next slide. This is where the piece is cut to length. It's pretty self-explanatory. Next slide. And these are dimensions taken. Periodically, dimensions need to be taken. The operators call in what are called offsets. In other words, how to adjust the mill down. Web off center is measured on the cooling bed. And again, the various parameters. Next slide. And after this, it goes to rotary straightener. This is a picture of the rotary straightener. And as any other part of the process, there's a lot of control going on here. Loads are monitored on each one of these rolls, and also what the entry temperature is. The next slide. And this is gag press material that doesn't get completely straightened with the rotary straightener. We'll go through gag press in a lot of cases, or if it's a heavier section, in some cases it just calls for gag pressing. In the picture on the left, that is camber being removed, and the picture on the right is sweep being removed. Next slide. And this is final inspection. Next slide. Now this you're all familiar with. This is your stress strain curve. and the yield strength being the point that you see on your test report that you do all your designs on and so forth. I know I don't need to spend a lot of time on this. It's kind of just more of an introductory slide for what we're going to talk about next. So next slide. Tensile testing. Again, two test specimens are taken per read. That is the ASTM specification. And there are always, ASTM also calls for shapes always being in longitudinal direction 1/3 of the distance from the flange tip to the web center. Next slide. And this is an example of A370. Most structural producers will take a full plate thickness rather than milling out like we call them a 505 rounds in a lot of cases. I believe about all your shape producers are going to take a full thickness specimen and milled down. The heat affected zone has to be removed if they're using, in all likelihood they're using a torch to cut out the sample, which we're going to see here in a minute, and the heat affected zone is removed. Next slide. And this is an example of a piece being harvested off the mill, piece being moved on the top right. Again, more equipment to move it. Now this lower, I guess this I guess I should have jumped right to this lower right picture where we have the torches cutting out the coupon. Again, ASTM specifies the web center to the flange tip 1/3 of the distance is where the longitudinal center of that specimen is to be, and that track torch is set a uniform 2 inches apart. That it always cuts a 2-inch piece coupon out of that flange. Next slide. And this is the milling machines. These milling machines are dedicated to mill off the same amount of material. In every case, ASTM, I believe, calls for 1/8 minimum. Yeah, that was on that previous slide that has to be milled off. And these are some examples, some specimens ready to be pulled. Next slide. This should be a movie of an operator doing the tensile testing. This is where the elongation marks are being placed. Placing it into the tensile testing equipment here. It's an extensometer which will measure very small, a very small increment of length change. And once the extensometer, once the yield is measured, once the yield point's been detected by where it's no longer linear, where the Young's modulus has been hit, and it's no longer linear, that's called the proportional limit, then it'll be pulled to failure. The extensometer needs to be removed so it doesn't destroy it. This is a sample being pulled to failure. Now we'll check the elongation. And it keys in the results. Next slide, please. Now, we talked about the testing and so forth. We're going to talk about how we arrive at the chemistries that we'll use. This is an example where we have one beam blank, but this one beam blank, you can produce all of the products of the 14 by 16 family from W14 by 145 all the way up to W14 by 398. Next slide. And that's done through grain refinement in a rolling mill. The melt shop, of course, gives us our vanadium, columbium, nitrogen levels that we need to process for those grain refiners to happen, and also the manganese. But work is another important aspect of what's needed. Products that don't have a lot of reduction on them. Yeah, products that don't have a lot of reduction on them would need more alloys. Next slide. This is an example where you have 18 different cast shapes, beam blanks, for example, and that would go into maybe 69 different product groups. and you might end up with 354 different final products. Next. If you look at the A992 specification, it looks wide open, but you can't use a W6x15 chemistry, the same chemistry for W6x15 as you would for a W14x370. So you want to use different products or different chemistries for different products. Next slide. Now, here's what happens. So you have process variation. For example, for W14x145, the LMF operators, they aimed for a specific manganese, they aimed for a specific vanadium and columbium in this case. And this is an internal chemistry of this producer to be Chem VNB. Now, if they take this same chemistry, the exact same chemistry, even from the same heat, and roll it to W14x159, they could find that they're getting close to this minimum yield strength. -3 standard deviations would be too close to the spec minimum. So whenever they, and that's fine, we're still meeting specifications, but the next, if we're going to W14x176, a new chemistry is going to have to be used. So the next slide. This is an example when you'd increase the chemistry. This one you'd increase the manganese, for example, and maybe the vanadium or columbium. Again, this is internal chemistry that this producer would use. And this same chemistry could be used all the way to the W14x211. And then if you go to the W14x233, I believe is the next foot weight, then you'd have to increase the chemistry again. Next slide. And 14x233 would be used for these, for another 4. Next slide. And all the way to W14x398. You could get by with just 2 chemistries, but what would happen is if you reduce your number of chemistries, you're always going to have to worry about what your weakest is going to be on -3 standard deviations. But if you got to worry about the 65 max, you'd have to worry about that W14x145 that we started out with. So you have to worry about, you're usually going to hit the minimum, and you're going to use multiple chemistries. Next slide. CVN test temperature testing is another important aspect of structurals. Next slide. And this is the Sharpie transition curve. Basically, it shows the nature of a lot of steels where the lower, as the temperature decreases, the steel becomes more brittle. Next slide. And these are various locations that Sharpie tests can be taken from. Next slide. And these are your typical dimensions of a Sharpie. Well, these are specified dimensions of Sharpie. Next slide. These are an example. These are machined out Sharpies. These are when they're cut to sections. And this is the 79. This is a broach. It'll make a 79,000th notch. Next slide. And this is where a periodic check of the notch geometry is taken to verify that it is within the ASTM specifications. Next slide. And this is the cooling bath, CVN tester, and the specimens being cooled. Next slide. And this is the a specimen being placed in the fixture, ready to be tested. Next slide. This is the tester ready to go. Next slide. And these are the important aspects that Shane covered. We keep the carbon low and sulfur low, and the rolling temperatures have to do their grain refinement. Next slide. And again, we're counting on that rolling mill to help us out on the grain refinement with the chemistries and the reduction. Next slide. And again, we use different chemistry aids to process, and there's process control. And if we want to improve Sharpie performance, we lower the temperature. That control rolling slide that we seen earlier, that's very critical when it comes to meeting Sharpie properties. Next slide. And here's a quick movie on CVN testing. This test being performed. There's a number of different views here. Test being removed from the bath, placed in the fixture. So, in summary, I hope everybody's picked up that manufacturing structural steel shapes, for the most part, is a controlled and predictable process. My saying I've always liked to say is that the steel producer knows what the test results are going to be when the scrap is purchased. Now, I guess we'll turn it back over to Brent.
All right. Very good. Thank you, Jim. Thank you, Shane. We are pretty tight on time, but I do want to start with a quick polling question before we get to some of the audience members' questions here. All right, so here is our polling question. Which of these elements will oxidize most readily in the electric arc furnace? Is it A, copper, B, vanadium, C, chromium, or D, silicon? You can go ahead and click on the radio button that you think is the correct answer. Again, the question is, which of these elements will oxidize most readily in the electric arc furnace? All right. I'm going to go ahead and close this poll. And skipping to the results, so Jim and Shane, about 70% people said D, silicon. What do you guys think?
Yes, silicon is based on, if you look at the oxidation potential graph, you'll see our chart, you'll see that silicon was the highest element on that list. As you went up on that, with those reactions, that the oxidation potential was greater. So yes, silicon is right.
Okay, great. We're going to get some questions in from the audience before we finish up here tonight. First question, if the steel is heat treated, won't the welding heat affect the strength once it's heated again?
Yes. Yeah, if you heat treat it, definitely changes the properties of the steel.
Okay. I'm going to take us to slide 19. The question is looking at the max carbon equivalent. Pointer out here, this line here. The question is, should that percentage sign be deleted here? Or is that a percentage?
The percentage, it is a sum of the percentage of carbon that's in there. In other words, when the carbon equivalent is calculated, it's just taking a denominator, so it doesn't become unitless. If you look at the carbon equivalent equation, that percentage should still be there.
Okay. All right, next question. The question is, I've heard that there are steel plates that are dual certified to be A36 or A57250, as well as HSS members that are dual certified for grade B or C for A500. How is the casting or milling of this member done for it to be dual certified?
Well, I can't speak for the HSS steel, but for A36 and 50 grade, it's very common with ladle metallurgy furnaces and rolling practices to be able, in the case of A36, to still hit the 36 minimum yield, the 58 to 80 tensile, and also at the same time hitting the 50, well, that'd be of A36, and at the same time hitting 50 KSI for A572 and the 65 minimum tensile. So with the chemistry controls and rolling practices, it's quite common to have those. As far as the plate grade that you're talking about, I'm not familiar with that grade, but I would say it's probably a similar process where you have overlapping chemistry and mechanical ranges, and I would have to guess that's probably it. Now, in the case of an A588 or an A992, because of the chromium max of 0.35 on A992 and the A588 chromium minimum, those two could never be dual certified, even though your mechanical properties can be very, very similar.
Okay, I'm going to move over to the Sharpie testing. We specify, this is coming from one of our audience members, we specify CVNs at minus 20 degrees Fahrenheit and minus 50 degrees Fahrenheit for Arctic projects. Can you talk about what you do to achieve that toughness?
Well, number one, we have to know whenever the order is taken that Sharpie temperature is required, and whenever we looked back at that control rolling slide, we want to get the finest grain that we can. We do that with low temperatures along with remaining reduction. So lower we get that rolling temperature, 1680 is common. That's one of our lowest ones we go to. But even lower than that is where you can really get that good grain refinement, the low temperatures, good grain refinement, and and the sulfur has to be down too. So I mean, those are what we would have to do. The problem is the expense on getting the sulfur down. It's hard on the ladle life, and the other thing that can happen is you have very high potential for breaking rolls at those low rolling temperatures. So that's how come producers would shy away from that. I mean, that isn't to say it can't be done, and it is done on some products, but the mill loads can get too high, and you're taking a risk whenever you're trying to hit those real low temperature sharps, the minus 50s. Minus 20s aren't as bad. They're pretty common anymore, but not on everything, obviously.
Okay, last question. I've got an image up here of the heat being poured into the ladle, and the question is this: how does the ladle not melt?
Right. The question there is, like I said, it's a steel-lined vessel, or steel vessel, but it's lined with refractory brick, almost a thickness of 12 inches all the way around. So that whole thing is bricked on the inside with a high-temperature refractory material. You can't melt it.
Okay. And then I think before we finish up here, we actually had a question that came in last week that I think was more appropriate for this week's session. And the question is this: if iron can have 8 times more carbon than steel, that being 2% versus 0.25%, why is it that steel is harder?
That's a very good question. We can teach a whole class on that. But if you look at the iron-carbon phase diagram, once you get above 0.76, you're in a whole different world with carbon and strength and microstructure. So our world is 0.76 carbon and down. Typically structurals are 20 carbon and down. Once you get into 2% carbon, you're into cast iron. There's so much carbon, you basically make a supersaturated iron grains with graphite flakes. As we all know, cast iron plates are kind of hard, but they're very, very brittle. So we stay in the steel world, 0.76 and below. Above 0.76 is called hypereutectic, and that's a world I don't even live in. So everything we look at is 0.76 and below. And it's microstructure as a function of carbon content.
Okay. Thank you much. Thank you very much, Shane. And thank you, Jim, as well, for your thoughts on those questions tonight. And thank you for a great presentation. We are more than out of time, everyone, so appreciate you hanging in there for the Q&A. because of the time limits here, I'm just going to let you know that you need to look through those last few slides regarding PDHs and quiz and recording for you 8-session registrants. All the information is there where you can find that, but look for emails in these coming days regarding reporting your attendance. Those of you who sign up for the individual sessions, and those of you with the 8-session package, look for an email as far as accessing the recording and the quizzes.